We are considering now vectors in the plane in the space. If we are talking about the plane, I have here my coordinate system with my x-axis and my y-axis, and then I'm going to consider a vector over there. I'll represent it in the origin, and I'm going to look at what the x-coordinate of the endpoint is and what the y-coordinate of the endpoint is. And I'm going to use that to represent my vector. So if P is xy, the position vector OP can be written in component form as xy. This is the component form. And it can also be written as x times the vector I plus y times the vector j, where my vector y is the unit vector in the direction of the x. So it's the vector 1, 0, and the j is the unit vector in the y direction, so 0, 1. So let's say this is, if one unit is 1 square, this is my vector I, and this is my vector j. And then I can obtain my vector OP as a linear combination of I and j, and that we can do for any vector on the plane. This can also be achieved in 3D, and this is also what we're going to do. This just requires a little bit more imagination for you to understand what is it that I'm sketching. Let's say here that this is my x-axis and my y-axis and my z-axis. Now I need to represent a point P with coordinates x, y, z. Let's try. It's just a little bit hard to see things in 3D. Let's say here. So I'm saying this is the point P, x, y, z. What does it mean if I project my point down to the xy plane? Then I will see here the x coordinate and the y coordinate, and then the height is giving me here the third coordinate z. Okay, this is not a very beautiful picture, but what I'm saying here is that in the same way I can write the position vector OP using the coordinates x, y, z. And I can also consider this in unit vector form. Sorry, I didn't write that in the first case, unit vector form. It's just that now I'm going to need 3 vectors. I'm going to need a vector I, which is going to be 1, 0, 0. I'm going to need a vector j, which is 0, 1, 0. And I'm also going to need a vector k, which is 0, 0, 1. So in my picture, let's say I is the unit vector in the direction of x, j on the direction of y, and k on the direction of z. And then I can write that x times I plus y times j plus z times k is the unit vector form for my vector OP. And we can find the magnitude of these vectors. Maybe it's more natural to say that in 2D we will just consider applying Pythagoras, x squared plus y squared, the square root of that. But this can also be extended to 3D, and we're going to need to consider the sum of the squares of the components under the square root. This way of representing vectors, either in component form or in unit vector form, and either in 2D or in 3D, is very convenient for doing operations with vectors like sum, subtraction, and scalar multiplication. If we want to consider, let's say, x, y, z as one of my vectors plus, I'll call a, b, c the other one, then I will need to sum the components. And this can also be written in the unit vector form. So if we have x times I plus y times j plus z times k for the first vector, and we want to sum the vector a times I plus b times j plus c times k, we can see that this is also written as if I were treating I, j, and k as variables. So x plus a plus y plus b plus multiplied by j plus z plus c multiplied by k. This will also work if we instead decide to consider the subtraction of vectors. We're just going to have minus sign in both cases. And lastly, if we wish to multiply by a scalar, so k is multiplying the vector written in component form, I'm going to need to multiply by k each of the components. And if I wrote my vector in the ijk notation, so let's say k is multiplying xi plus yj plus zk, then I'm going to need to multiply k by x and k by y and k by z.